Hi, this is Beth Faber at the Hydrologic Engineering Center, and this is lecture 3.6 of Prospect Course 209, Risk-Based Analysis Using the FDA Software. This lecture is on uncertainty and exceedance probability functions, or in frequency curves. Names on the screen are some folks, in addition to me, who have contributed to this lecture. I'm going to start off with some motivation for this topic before we even get into an outline. This is a frequency curve developed from about 56 years of data, right? This is 56 years of annual maximum stream flows that have been sorted and plotted versus plotting positions in red, and then with an analytical probability distribution fit in black. Right? The horizontal axis is exceedance probability with 0 to the right. So it's a cumulative probability distribution. I'd like you to look at that and consider how good you feel about this data and this estimated model for fitting this data. Okay. Doesn't look too bad. Maybe you did a workshop yesterday, I think, in which I gave you a data set and had you fit a couple of distributions to it. And at the end, you found a distribution that looked like it was a real good fit, and that felt good, right? This might feel okay. I'm saying maybe the distribution fits well in the middle. Those three highest points are a bit higher than the model would have predicted. Same thing with the lowest points, are a bit lower, but overall not too bad. And as engineers and economists, generally if our data and our model match pretty well, we feel pretty good, right? So maybe we feel okay about this. So what I'd like to do is just wreck that good feeling that you're feeling right now, right? Just wipe it out. I want you to feel uncertain about this, right? And I'll show you why. So we're going to do a statistical experiment here. So this is a Monte Carlo simulation. It's a bit like having Excel roll six-sided dice for us, like we did yesterday, right? So I'm going to do a statistical experiment where I sample data from a known probability distribution, right? And then try to re-estimate that probability distribution. So here's a known flow frequency curve. I'm specifying this flow frequency curve in blue. It's a log Pearson type 3 with these parameters. And from this known probability distribution, I'm going to take 1,000 random values and produce 1,000 years of annual peak flow. Okay, so this is data drawn right from this probability distribution. Now, since I've plotted flow on a linear axis, I've redrawn the probability distribution on a linear axis instead of a log flow axis, so it makes a little bit more sense with the data that we've randomly sampled from it. Now, on our original probability distribution, the 1% flow is here at about 200,000 CFS. So here's the 1% flow or 100-year flow plotted against the data. And if you think about the 1% return period, that means that this flow should be equaled or exceeded on average every 100 years. So in 1,000 years, it should be equaled or exceeded about 10 times. And we see 1, 2, 3, 4, 5, count him, 6, 7, 8, 9, 10, 11, right? So a little bit over, but about right. Here is our 500-year flow at about 450,000, and it's exceeded twice in 1,000 years, right? So that looks about right. So now we're going to estimate the entire probability distribution, and then we'll pull from it the 1% flow, okay, across the 1,000 years. So what we have happening here is that every year I'm adding that flow to the sample and re-estimating the probability distribution and pulling off the 1% flow. And every year as I walk across the record, I'm adding in one more value and re-estimating the distribution and plotting the 1% value, moving across. So in this case, what we know to be the true value is this dashed line, just over 200,000 CFS. And if we look across our 1,000 years, well, it takes quite a long time to converge to our known right answer of 200,000 CFS, right? 700 or 800 years, right? Back here in 1 or 2 and even 300 years, it's not so good, right? That's disappointing. And what's happening here? So when a big event happens, like this one, it shoots the estimate of the 1% event way up, right? What's happening is we compute the probability distribution from our mean, our standard deviation, and our skew. And when a big event happens, the mean goes up, the standard deviation goes up, right? So the curve goes higher, the curve gets steeper, and then a positive skew coefficient, which we'll get with a high value, makes the curve up, right? So all three parameters are going to be shifting to a higher flow for the 1% event. So a big event happens and our 1% event shoots up. So it happens here. Here's another value shoots up. Hope you can see my arrow here. Here's another big event, shoots up. Time goes by without a big event happening, and the skew coefficient goes back down, the mean and standard deviation go back down, so the estimate gets lower, but then another big event happens and it shoots up again, right? So think about when we usually re-estimate a flow frequency curve, right? We usually re-estimate it after a big event happens. And what we see here is that a big event and the increase in the 1% event that it causes might lead us closer to the true answer, or it might lead us further away from the true answer. We really don't know. But what we do know is that the estimate we get at that point is going to be one of these high points. And if we waited a few years longer and recomputed, it would be going down, right? What's happening with these big flows out here, right? We have little bounces in the frequency curve. It jumps up, but not nearly as much. So what's happening with these? Well, think of this like your GPA in college, right? Back here is your freshman year GPA, right? Every class you take and every grade you get bounces it up and down, hopefully up. And once you get out here to these later years, this is like your senior year GPA, right? You've got so many classes already in that average that any additional one is not going to change it very much, right? So what's happening here is we have so much data that any individual data point is not changing things very much, right? Back here, every individual data point still was changing it a lot, right? So that's relevant. Now, why do we have a couple of big events happening in such a short period of time here? Right? This is called clustering, and this is a characteristic of true random samples, that we see clustering. We see a lot of events. We see events that are similar, or similar outcomes can happen close to each other, right? And then not happen for a long time, and then more similar events that are close to each other can happen, right? True random outcomes see clustering. You know, we expect them to be maybe evenly spread across the sample, across time, and really they aren't. The random outcomes are rarely like that. If you do any gambling, then you've witnessed this clustering. You know, you have hot streaks and you have cold streaks, right? So a true random sample does experience this type of clustering. So let's say this is 1,000 years, right? This is not real data. This is randomly generated data, and I'm going to back up to the previous slide for a second. Then down here in red, I mentioned that in this experiment, the assumptions of a frequency analysis are true. So we're looking at a best case here. You know, in a frequency analysis, we assume what's called IID, which stands for independent and identically distributed. This means each data point is independent of every other. And then the second ID, identically distributed, means all of these points come from the same probability distribution, right? They come from this probability distribution that I started with and sampled from. In reality, the identically distributed assumption is often challenged, right? A long period of time, the watershed or the climate changes across time, might not be identically distributed. They might not be identically distributed. But in this experiment, this is best case, right? In this experiment, all of our assumptions are true. So what we're seeing is kind of a best case of the uncertainty, at least amount, right? That'll be more important in a moment. So let's say this is 1,000 years, right? And instead of considering how things look moving across the 1,000 years, let's consider where we might exist, or when we might exist in this 1,000 years. What if we and our gauge are observing stream flows in this period here, right, between about 650 and 750, right? If this was the record that we had observed with these big events happening, we'd think that big floods are really pretty likely, right? We've seen a lot of them, and they can probably get even bigger, right? So if we experienced this period of time, our frequency curve would be pretty high, and we'd think big floods were really likely, and our estimate of the 1% would be pretty high. Right? What if instead we lived in this period back here, right, from about 325 to 425? Okay, if we observed this period of the record where no big events happened, we'd think big events were really unlikely. You know, maybe that can't even happen. Right? The frequency curve we estimate from this 100 years would be quite low. right? And the likelihood of seeing something this high, if we even extrapolated our frequency curve that far, would be a pretty small probability. And our estimate of the 100-year flow would be pretty low, right? So if you consider where we exist within this 1,000 years, the picture looks very different. So on the next slide, I'm going to show a moving 100-year record. So instead of the record increasing as we move across the 1,000 years, I'm going to always have 100 years, and I'm just going to have a moving window going across and estimate the 1% event with the 100 years at a time. Right? So here's my moving window. It's 100 years wide. So you can see here, I start here at 100 years. Here's where I pick up this big event. And moving across another 100 years, here's where I drop that big event back out of my sample and move along without it. So each of these 100-year flow estimates is based on exactly 100 years. And as we expected, when we've got a period where we've included these big events, our estimate of the 100-year flow is really high. Back here where we didn't have any big events, the estimate of the 100-year flow is really low, right? So what we're looking here is the span of our uncertainty in trying to estimate this probability distribution from only a 100-year sample. And we think of a 100-year sample as pretty big, right? We think of that as a lot of data. And this is showing us that we can be remarkably wrong with 1,000 years of data. All right, so what's going on here? What's the problem? The problem is that some of these time periods are very much not representative, right? These samples are not representative of our population here and here. In fact, a lot of the time, our sample is not representative of the population. Occasionally it is, right? There are times when the sample gives a reasonable estimate. There are times when the sample gives a really terrible estimate. And 100 years is a lot of data. What if we only had 50, right? What if we do this with a 50-year window instead, right? Well, my low estimates are even lower. My high estimates are off the chart, right? I have even more uncertainty if I only have 50 years of data moving across this record, right? So the problem is not that our data is wrong. It's not that our model is wrong. It's that we have a sample that's unrepresentative of the population, right? So here we are again with our data and our sample. And like I said, it's not because the data is wrong, and it's not because the model is wrong, and the model agrees with the data. The problem is this might not be a representative sample, right? So let's consider the uncertainty that we have on this sample. Now I've moved from a linear scale back to a log scale, so the uncertainty looks a lot narrower. This is also a different data set, but keep in mind that in log space, this is actually pretty wide. So these PDFs, which you should visualize as coming out of the screen, these represent uncertainty in where this curve actually lies. Note that they're positively skewed, so they reached further high than low. And at the low end, they're going to be negatively skewed, so that long tail is going to point towards the bottom. Right, so these curves coming out of the screen represent our knowledge uncertainty in where this curve is. So area under these curves is probability, representing our uncertainty. And if we want to span 90% of the middle of this distribution, and knock 5% off of the upper tail and the lower tail, we can draw a 90% confidence interval all the way across the distribution based on the PDF that exists describing the uncertainty at each quantile, right? So here's our 90% confidence interval. So this is two different representations of the uncertainty in our frequency curve. And I hope that looking at that artificial 1,000-year record with the best case estimation of doing a frequency analysis based on a sample of data, I hope that now you have a feel for why we have so much uncertainty in our frequency curves. Okay, so now finally I'm moving into the objectives of the presentation. Understand the nature of uncertainty in a flow frequency curve. We just looked at the main cause of that uncertainty, which is called sampling error, our sample perhaps not being representative of the population. We'll discuss ways to develop a flow frequency curve and the sources of uncertainty in each method. So the method that we just looked at, which was flow frequency analysis, and also other methods. And then we'll review how to enter this information into FDA. Right, so the way we'll structure the talk is, first of all, where we get the flow frequency curve, and we'll look at two different methods. We'll talk about the frequency analysis method, and we'll talk about instead doing hydrologic modeling of the watershed using frequency-based precipitation events. We'll talk about why there's uncertainty in the curve in each case. There's more sources of uncertainty than just the sampling error. We'll talk about how the uncertainty is described in FDA, And then we'll look quickly at some situations that are challenges to those primary methods and also to the typical FDA inputs. Right, so the two approaches we'll look at, as I said, are the frequency analysis of gauged flow observations. Right, this is the preferred method if we have a streamflow gauge at our site of interest. Right, so when we have flow observations, we'll use the frequency analysis method. Right, the next method we'll look at is hydrologic modeling using frequency-based precipitation. We'll use this one when we don't have flow observations at the site of interest, or when we need to model a complete watershed. So maybe we have flow observations at one site, but we need to have frequency curves around the watershed that are all consistent with each other. Right? Or we might use this method when we need to capture changing conditions in the watershed. Right? So we need to be able to model those conditions and model how they change. Right? So this talk is going to be divided into 3 videos. If you have questions about those motivation slides, please go to the discourse site and type those in, and I'll try to be there at the time I think you're watching the videos to answer those questions. Right? The next topic we'll talk about, or the next video, is going to be on the observation approach, or the frequency analysis approach of estimating flow frequency curves. So that's the end of this video, and I'll see you at the next one.